Okay, so what I want to do today is I want to keep on going over that derivation from the same point of view we had before. That's not all what I wanted. So what we had before is we derived the spatial metric. ds squared equaling this dr squared, 1 minus r squared over a squared plus r squared d omega squared using basically x squared plus y squared plus z squared, w squared equals a squared, and dx squared plus dy squared plus dz squared plus dw squared equaling ds squared. So we use this, and then we convert it to, and then we, and then also then the x equals r sine of theta equals pi, y is r sine of theta sine of phi, and z is r cosine of theta. So we said if you do all this, cranking this, ton and tons of algebra, you end up with this equation here. And then we said that for our universe, what we're going to do is we're in co-moving coordinates, so the time is a proper time. So we said for our model of the universe, this is our time. And the universe is expanding. And so the way we're going to expand this is we're going to put in some parameter to indicate that the universe is expanding. Using the notation that, using the notation that Sean Carroll is using, he calls this capital R squared, some function of t. And then he puts in the spatial coordinate here, and he puts in this guy here. He puts in that. And just so you know that in the Carroll's book, this 1 over a squared is at curvature here, okay. And so this is one metric. What I want to do is get this exact same metric from a different argument. So we want to repeat this stuff. We want to repeat this derivation. Okay, from another point of view. And so the other point of view is going to be this, is that we wanted the metric for a homogeneous isotropic space, and we wanted to have maximum symmetry. So the other argument was this, is we asked what is the maximally symmetric okay, what were the notes? What letters did we put down here?
Oh, for
Was it just IJKL? Or
yeah.
Okay, so we had I, J, K, L. We asked what was that. And we said, well, if it's going to be, this means that your space is isotropic and also homogeneous. And what we did is that we wrote this as a series of Kronecker deltas, and we said in this, the spatial coordinates of Kronecker delta is the same as the metric for flat space, the spatial part. And then we said, well, that's what you'd have if you're in locally flat coordinates. So then we generalized to the G's. And so when we did all that, we ended up with, okay, we had some K here. And then what was the order of the indices we had here? We had 4 G's here, and I honestly don't remember this. I think this was I, this is K, and then this was, this is J. This is J, and then this was K, and then L.
Yeah.
And then this would have to be J, then I here, and this would be then J, K and L.
It's IL Shit, Earth.
No,
No, wait, no, that works.
okay, is this right?
Yeah. I just have the G's swapped.
Okay, so let's do it the way. So it's just it'll be the same in notes. So this is our IL. This is our JK.
Yeah.
Is that what we have?
Yep.
Okay. So we had that argument here, and then we did one other thing. We looked at the Riemann curvature tensor for this. The Ricci tensor for this. We said if we look at R, and then which indices did I have?
We summed on I and K.
Okay, so we summed on I and K, so this is going to be then J and L. So this is 2K G J L. Is that all good? Good.
Yep.
And then what did we say if we wanted then the Ricci tensor, scalar tensor?
We sum on J and L.
And what did that give us?
We got 6K.
Did that give us 6? So we have this. Okay. Now we want to do so we have this here. Now I want to go through and figure out how we can figure out the DS from this. So let's ask, so we have to keep this in mind. So let's ask, what must ds squared be if we have a spherical model that has that is isotropic and homogeneous. And this is actually really clever. Okay, so we have to do a little bit of recalling here. So recall. Okay. Recall when we first studied. I did start that, didn't I? Oh, good. How did we first study the short strip line? Okay, how did we do it? We wrote this ds squared to be minus e to the 2 alpha. Alpha is a function of r, t squared. There's a c in here, but I'm going to set the c to 1. E to the beta r, e to the 2 beta. Beta is a function of r. And then we had our dr squared here, plus our r squared, d omega squared. We had that. And then what did we do? In a homework exercise, you calculated all the Christoffel symbols. So you calculated all these, and then from these, you calculated your R units. You calculated all those. Yeah. Okay. So these we have. We already calculated these. Okay, so what we want to do is, and again, what is this problem here? In the short-shell black hole, this is a spherically symmetric model. So this model here is spherically symmetric. So what we're going to do is, if I wanted to have for my universe to be spherically symmetric, what am I going to do? So for our universe, I'm going to basically just do. I'm going to have this. And then I'm going to have my spatial board. And what is this going to be here? Well, it's basically just going to be this part right here. Because that guarantees spatial symmetry. So what we're going to do is we're going to take all these expressions we have here. And all I'm going to do is set alpha to
0.
Exactly. I kill my alpha term, that's going to make this 1. And then I have all these here. So I can just copy down what these results already were. And then what can I do? Well, I can take this solid here and then match it up to this one over here. Done. Okay, really a pretty slick idea. So let's actually do this. So let's write this over here. So what we're gonna do is take our pre-existing argue new expressions. And set alpha to 0. Then what happens is e to this term here then goes to basically goes to our problem. And so I'm just going to copy down the one result we need here. So I handed out that one sheet that had all them all listed. I said bring that. I don't know if you brought that or not. But I am prepared regardless. I have them here, and I even have my glasses. This is good. So if you do all that, we need this one here. Okay, and then this reduces to our problem to what?
The final term.
Yeah, this goes out, this goes out, this goes out. Where do I set to this guy here? And we're going to equate this to, no, I erased it. So I had this expression here. What was it JL? JK?
JL.
Yeah,
JL.
JL? Yeah. We're going to equate it to this. So this is, I'm going to put in this here. I'm going to put in this 2K GRR. And okay, what was this GRR? From over here? Is it e to the 2 beta?
Oh yeah.
Okay. That gives us that. Okay. Well, that's for the most part pretty easy to solve. So what happens here? Well, the 2's go out. So that gives me here. And what does that give me? This gives me it's just this. This we can integrate more slick. So this side over here gives me k squared, kr squared over 2. There could be some constant here that we have to figure out what that's going to be. And what does this side over here give me?
That's 1 over. Yeah, well, -1/2 e -2 beta. Yeah.
Because if I take a derivative of this with respect to beta, it pulls on the -2, and that gives me that this here. And so the 2's go out. Okay, so let's see, we'll count the 2. So this gives me this minus e to the -2 beta equals kr squared c. And this is going to give me minus 1 over kr squared plus c equals e to the 2 beta. Do I agree with that? I think that's true, right? Yeah, I think that's fine. Now what's going to happen here? The question is, what is c? So if we go back to our metric here, let's go back to, so we have this metric here. It's going to be now, if your k is equal to 0, what would it mean about the space we have? And think about what it means about R. Our R is
R is 0. So
yeah.
it's flat space.
So we have flat space. So if we have this, our R, JK is 0, so our space is flat. And then what does that mean if we have flat space here? It means that this e to the 2 beta then, in that case, it better be what then?
It better be 1.
It better be 1. So therefore, this when n equals 0, the c to the beta r here, and I'm sorry, this 2 beta, it better be 1. Because our ds becomes this fellow. Right, and this is just spatially flat space and spherical coordinates. So this is just the flat space metric written in spherical coordinates. Okay. So in case, what does that give us here? So this gives us minus 1 over 0 plus c equals 1, or it tells me that c must be
-1.
minus 1. So we have this e to the 2 beta here is 1 minus 1 over kr squared minus 1, or what it's always written is 1 over 1 minus kr squared. Okay. And this really is our GRR term. So we're left with basically the same thing. So what we have here is this guy here. Just goes to our 1 over 1 minus kr squared plus r squared d omega squared. And this is the same result as Ohanian's method. So we get the exact same result. You can see that it makes a connection of this k here is going to be the 1 over a squared. I'll just say where the k is this 1 over a squared. Okay. And so what do we do? Well, the fact that the universe is expanding again, we're going to put that expansion in my hand. And so what we're going to say is that we're going to be left with this. We're going to be left with this plus r squared of t. And this is our expanding universe here, because basically that's from the observations due to Hubble that the universe is getting bigger. And then this is going to be our metric thing. I mean, the whole thing's a metric. That makes sense?
Yep.
Questions? Okay. Now there's just if you go and look at that handout that I gave you from Ohanian, I just want to do some name changes here. I mean, not from Ohanian, from Carol. So Carol does a couple name changes. Okay, so Carol is going to do this. So Carol redefines several terms in this metric. Basically put it kind of the standard form here. So the first thing he's going to do is he's going to okay. The one thing is that he actually calls this he puts little bars in the sky. He's going to do a little change here. So to begin with, okay, just to keep consistent with his notation. So to be consistent, so no. I will change R to R bar to match up with Carol's notation. So if I rewrite that, I'm just going to put bars on things. Okay, we're going to go right back to R in just a moment. But just this is just so you can match up and you can read what you have in Carol's book. So if I rewrite this, again, I can call that any variable. No, it's just up there. I was going to do a couple of defining things here. He's going to call, he's going to define A of t to be by definition R of t over R0 here. And this is going to be R at some fixed value of t. This guy here, this A here, this is often this A of t is written as capital S of t. So if you look at some books are going to have a capital S of t, it's going to be the same idea here. This is called a scale factor. And all it's doing is basically this expansion rate is actually going to change with time. And so what you do is you fix some time. Currently, this time is R2. So usually anything in astronomy, cosmology, anything with a 0 on it usually refers to R2. So this would be whatever the R value is at basically R time. We don't know what it is. And this is going to be the R at some other time here. So what we're going to really worry about is the ratio of these two. Basically, how does this here in the state here vary, compared to R time? So if you're to look at the present time here, if T is T naught, this A here is 1. Okay. So we're going to calculate how the scale factor is going to overall change over time. That's what we're going to do. So when you get these equations, what we're going to really solve for, we're going to really be solving for how the scale factor changes. Okay, that's how these things will work. So that's the first change he has. And now what he does, he goes back to an R coordinate. So now he says, let's go back to an R coordinate here. He's going to call this to be R naught times our R bar. So now he defines this R to be here, and then he defines as a kappa here. This is kappa, which is going to be this K, okay, over R naught squared. If you do that, you basically end up with this. I'm not going to go through and do the substitution. You can do what you want. If you make these substitutions here, In other words, so this R bar here, you're putting an R over R naught. Put that all in here. What happens is this whole equation here becomes ds squared equals minus t squared plus a squared here of t times, oh, am I getting off the board? I think I can squeeze it. Okay. 1 minus kappa r squared. The dr squared here plus r squared and x squared. So all it was basically this is the way this equation is almost always written. And all it was, it's just changing variables. Don't be. We haven't done any new physics here. The only really new thing is we introduce the scale. Okay, does that all make sense? Now this one right here. Okay, when I was going through, it always used to be called the Robertson-Walker metric. And then eventually people realized what there was a Russian physicist by the name of Friedman who did a lot of early work on this. And then there's the Friedman-Robertson-Walker metric. And somebody said, you're forgetting about Lemaitre, who was a Belgian priest who actually did work contemporary with Friedman, who came up with the whole idea of the Big Bang and stuff like this. And says, you need to include him. And so this becomes a Friedman-Lemaitre Robertson-Walker metric. Okay, I'm probably just going to call it the Friedman metric or the Robertson-Walker metric, or just because that's what it is. So this is often the Friedman. Is it IE or EI? IE. Why not have two ones? Here. Okay, Lemaitre. Really? Girl should have his name there. Lemaitre. Robertson. Walker. Metric. With Lemaitre, there's actually one of the famous Einstein stories is at some point Lemaitre did his calculation and it showed that basically the universe was expanding. And he showed his work to Einstein. And Einstein says, well, your physics is impeccable. I mean, your mathematics is impeccable, but your physics is atrocious. Because Hubble had not come up with the expansion of the universe yet. So there was actually a prediction done by Lemaitre, and then not shortly after that, Hubble came up with his observations that the universe was expanding, and Lemaitre was right. Questions to this? Okay, so what we're going to do is we're going to be using these equations, this metric here, to basically get a lot of our. That makes sense? Okay, let's do a little bit more. Okay, now I would like to do a little bit of cheating if you don't mind. The cheating is, and it's not that big of cheating. Okay, I'm just going to state what the Christoffel symbols are for this, and then also then what the Ricci tensors are for this. Is that okay? Because I mean, you know how to calculate them all, and there's nothing hard about it. I can have you calculate a couple of these. So I'm just going to. Did I give you the page? I give you the page. Okay. Do you have page 332? Or 333? It would be that one packet on the bigger packet. No, not the one I gave you one from Carol.
Oh, I think you have that. Yeah.
Yeah, so does it have pages 332 or 332?
Yep.
It does? Okay. So if you look there on page 332, there's all the Christoffel symbols. And then if you go to 333, it has the curvature tensors, the Ricci tensors. Okay, I'm just going to use those. Is that okay? Because I don't. It's not. There's not any new physics you're using here. The hardest part to remember here is that if I were to ask you what GRR is, I mean, this is going to be the hardest part. What is GRR for that? Okay.
A squared T over 1 minus kappa R.
There, you've done the hardest part. The hardest part here is remembering to put in the superfactor here. Because it's really easy. Here you can see the GRR and you can think, oh, well, right, here's your here's your DR squared. So this is your GRR. Not quite, because you have that factor coming in here. So you just have to remember when you do this, is that this is this A squared 1 minus this kappa squared. That's going to be the hardest thing to remember. Other than that, there's nothing complicated with this. It's just standard calculations here. Okay, so with that said, if we put this into the Einstein equations, so remember the Einstein equations are this. Now, first of all, what did we do that crazy factor of C?
That equal 1.
Yeah, we set our C to 1. And then what did we do? This G mu nu is this R mu nu minus 1/2 R G mu nu. And that's equal to this. And we figured out what this R was equal to. How did we figure out what that R was equal to? We did something. Good review. We multiply both sides by let's say G mu nu. Or actually, let's do the steps. Let's multiply by G sigma mu. What does that give for me? This becomes
R sigma nu.
This becomes R sigma nu minus
1/2 R G sigma nu.
this is 1/2 R G sigma nu, which is a
It's Kronecker delta.
4-dimensional Kronecker delta.
Yes.
8. Oh, that's a set 8. 8 pi G T sigma nu. And then what do we do with the sigma nu?
Set them equal to each other.
We set them equal to each other. So this gives us R minus 1/2
4R.
That's right. 4R equals an 8 pi G T. So this is minus 2R and R here. So this is minus R equals 8 pi GT, or R is 8 pi GT. And so I can put this into here. Move the minus sign here. That goes into here. This gives me an R mu nu plus 8 pi G T over 2 G mu nu. Yes, I know that's 4. I'm going to leave it like this though. That is 8 pi GT mu nu. Am I still on the board? Yes, I am. And so this tells me that R mu nu is 8 pi G T mu nu minus 1/2 T G mu nu. There. That's the equation we're going to solve. And we have the left side is basically we have all the components of the Ricci tensor that Carol's worked out for us. So that means we need to know what is what is T mu nu for basically our universe. And what I'm gonna do is I'm just gonna state that, but I'm gonna call, I don't want to get too far ahead without Jacob here. The next point is not hard, but I just want to do here. Well, not everyone, because it's just gonna be you and Jacob. So let's see. All right, so we will see on Monday. That for a perfect fluid. And a perfect fluid is basically going to be one that has there's no viscosity in it. There's no, it's going to be isotropic and everything else. This T mu nu is going to become your mass density plus your pressure. Okay, this is your pressure. Times mu nu. Okay. Oh, you're good one. Okay, so let's get with the C. We will see. Okay. Then you're going after this?
No, I'm gonna watch the video tomorrow, but I figured I could
Okay.
observe. Our practice just went late. We're not leaving something.
Oh, okay. I completely misunderstood. So we see. Okay. Maybe we can make that better relation. We will now see. We'll now show that for a perfect fluid, that we're going to end up with then G mu nu. Okay, where for co-moving coordinates, u mu is going to be 1, 0, 0. So what I want to do is actually then figure out what this is, what we're going to do. So we're going to take that, put it into our Einstein equations. We have the Ricci tensor here, the Ricci tensor, so then we can actually then figure out how our universe is going to be scaled. Make sense? Well, let's go through and see how that works. Now do a little bit more, okay. Further. Okay, the T, if I make them upper like this is going to become, when we're all done with it, this will become rho 0, 0, 0, 0, 0, 0. Then we're going to have pressures down the side. Along the diagonal. That's what our T mu is going to become then. Okay. That's what that'll be. And then what will that mean in this? Oh, and it should have with a G11 here, a G22 here, and a G33 here.
Like rho squared plus EG11 squared.
Okay, so this will become G mu nu T mu nu, right? What does that make this then? Okay, what is the G00 component here?
1 or negative.
-1. So this will become -1 times the side row. Plus then what's gonna happen, you're gonna have this times 1 in space. Right? This term here won't contribute. Because basically these are all zeros. So you're just gonna have this guy contributing here. That makes sense? So this will become G U nu. Again, if I wrote the other version of this here, I don't know why I wrote it like this. The other version of this is just everything raised up. That's just for everything raised up. Let's see, look at this. Uh-oh. Oh, we're good. So what is this?
So
You have to be careful. I kind of wrote this badly.
Omega delta.
Yeah, this right here, the reason I wrote it badly is tell me why this is actually written much better.
Oh, because you already did the time.
We already did the zero component. These are actually not just the spatial components here. So this is really this. So what does this become? That's a Kronecker delta of this guy. So what does that equal?
3T.
So this guy here, this T right here, that T here is really 3 times the pressure minus 4. That's what that's going to be. And so we know these fellows here. You know, this fellow here, we can actually start getting things. Make sense? Let's actually do one because to set this up. So let's look at R11. Okay. So if we look at R11 from Carroll, what do we have? I should know R00. So R00 with Carroll is minus 3 A double dot. What do you think A double dot means?
Second derivative of time.
Second time derivative of the scale factor though. Okay. It's going to equal what? According to this, it's going to be 8 pi G. Okay. What is T00? It's not quite rho, it is minus rho. Then minus or 1/2. Okay. RT, which is my buddy here. Okay. Times G00, which is
G0.
right. So you're doing
Or that's negative 1.
that's another -1 here. And what does that become? This is 8 pi G. Okay, let's see. I'll get a comment on here. I won't get a comment. Yeah, well, I'll get a 2 and 2 here. The right, this is -2 rho, minus 3p plus, actually, this comes in the plus, that comes in the minus 2. Did I do that math right? The minus and minus make a positive here, so they're coming out with here. I'll put top on here by 2, that is good. The 2 here cancels this here, so this gives me 4 pi G. And what am I left with? This, and I can get a 3p minus 3 rho. Get rid of the factor of 3, and this gives me that equation. Okay. Now if I wanted to do the 1-1 case, what would I do? I have to do the exact same thing. So we'll hold that off to Monday. I will prove this expression here for our perfect fluid. And what we're gonna do is once we do look at the R11 equation, we're gonna combine the two equations together. And that's gonna be the main equation that's gonna govern how our universe is gonna expand once we put one of the things though. So we're gonna be able to actually figure out how the size of the universe is actually gonna change based as a function of the history of the universe. And what's gonna be important here is that this row here kind of give you the game away. This row here is going to be the play dominant row. So this row here is going to have a couple pieces. It's going to have the row of matter. It's going to have the row of dark matter. It turns out that, okay, first of all, what does it mean to be dark matter? Why is it dark?
Can't. Like it doesn't emit light.
It doesn't interact with the light at all. So the reason why it's dark is that basically you have some sort of matter that doesn't interact with the light. So what does light need to interact with? Go back when you're doing the particle physics section. Photons interact with anything that has electric charge. Okay. So whatever this dark matter is, it can't have electric charge, otherwise it would interact with light, and you can see it. So people are speculate whether it's neutrinos. The neutrino hypothesis is probably not the case, or at least most people don't think it is. I think it can be, because I think there's a different type of neutrino. Okay. When you actually set up the electroweak theory, which is what governs this, is that if you remember, I said that the neutrinos are only left-handed components, because that's all these W particles interact with. Well, if that's the only thing that these W particles interact with, you could just as well have a right-handed component. And the right-handed and left-handed components do not have to have the exact same mass. And so you'd still have a right-handed neutrino, which would be more massive, which would interact gravitationally, that would not interact with light. So I think it's just end up being other components of I think it ends up being the right-hand component of just neutrinos. That's just me. The current contender for this is something referred to as axions, which is actually something coming from quarks. When you look at the Lagrangian there's a very, very subtle phenomenon that's predicted, referred to as an axion. These could be massive, maybe they're not. But we're gonna have a dominant case that this would be basically that this is these are axions. I don't think it is. I just think it's right-handed neutrinos. That's just me. Okay, then what else do we have? You have photons. Okay. And then the one that now people know, well, or at least speculate that it's there. Dark energy. Okay, so what is dark energy? I'll actually ask you a trick question. No one knows what it is. Okay. It appears to act as just a constant that's always there. So the bigger the universe is, the more you have of it, because basically it's a constant. And what it's going to do is it's really going to function as a repulsive gravity. And if there's more of it, then you get more repulsion. And so what's going to happen here is as the universe gets bigger, this gets smaller because the space you only have so much mass. The volume gets bigger. This gets smaller. This gets a lot smaller because it turns out this is one over the volume, one over that length scale to the fourth power. But this is a constant. So as the universe gets bigger and bigger and bigger, these play less and less of a role here. This plays more dominant. And this will actually end up acting like a repulsive gravity, which causes the extension of the universe to just take off. Meaning it's kind of an exponential growth. And people currently think this is here, although, okay, just so you know, in astronomy, there are measurements and then there's measurements. Astronomy measurements kind of come and they kind of go, because okay, they're measuring hard things. And so we'll see. Okay. Right now, most people say it's there. They say it's measurable. I think some people would wonder whether the measurements are right or not. I don't have a dog in this fight. It doesn't bother me one way or another. Okay, let's say I don't like that term. It doesn't matter. It's still there. I can like this term and it cannot be there. It doesn't matter if it's not there. And whether I like it or not, it's just called reality. It's going to be what it's going to be. Okay? We're done.